All right, good morning. I think we will start. Some of you might already stay home. Uh, so far, I gave you three examples. Okay, first two examples are energy transport when there is no movement of fluid. Okay, the first example is pure conduction. Second example is conduction and convection, but you use neutral law cooling to assume or transfer the equation into conduction equation. All right. Last time we met, I gave you another example. In that example, flow works dominate. When flow work dominates, you may create a hot spot in your system because flow work is a means of giving energy into the system, right? And that increase in energy by means of flow work is called viscous heat. Last time we discussed about that. For today, I'm going to give you another example, okay? Last examples, we discussed that we have two transport phenomena taking place at the same time. We have momentum transport and energy transport. Last time we discussed which one should be done first, right? Theoretically, it must be solved simultaneously, but by complication of the math, we cannot do that. So we have to start somehow. Last example, we start with momentum because we can assume that physical properties such as density and viscosity are not a strong function of temperature. In that case, we can solve momentum equation as if the system is isothermal, and then use velocity profile, plug into the equation for energy to solve for temperature profile. That was last example. For this example is an opposite thing. And this example is basically closed system. Okay? Inside you have liquid or fluid. On one wall, temperature is high. The other wall, temperature is low. Okay? If you consider fluid in contact with high temperature wall, of course, fluid should have higher temperature as well. So if you imagine temperature profile, there's supposed to be high temperature around here, low temperature around there. And normally, fluid with high temperature usually have low density, like air. When you have hot air can rise so that you can have balloon, right? In balloon, you you heat it up air so that density of air is lower so that the balloon itself can lift. In the same manner here, hot fluid here should have high temperature so that density will be lower and it moves up. On the other hand, cold fluid here should have higher density with respect to fluid on the left-hand side. So therefore, it sinks. Okay? So there will be somewhat like circulation of fluid. Hot fluid going up here. If this part is not heated, it will cool down and recirculate back there. When it's down here, it's touching with cold wall, density sink down here, and it's recirculated. Okay? So this is what we call natural convection. There's a movement of fluid, but not by external force, not by gravity, but the movement is caused by differences in density. Okay? So, in order to avoid any complication, we will consider just the middle part of the system, and that will be that picture. Okay, so just keep in mind that the system is closed system. Right? Now, inside here, there will be a movement. You can imagine that around here, there should be fluid moving up. On the right-hand side, there should be fluid moving down. Okay? So according to our common sense, if the fluid on the left is moving up, fluid on the right is moving down. Fluid in the middle supposed to have 0 velocity. So therefore, we set up the origin point here at the middle. Okay? But x or z would go up or down, that's arbitrary. It doesn't matter. So according to the text, they put z-axis going up, y-axis to the right. Okay? If you imagine temperature profile, then it's supposed to go down from the left to the right. It can be linear, it can be non-linear. Okay? If you imagine the temperature profile to be linear, that means you are ignoring fluid movement. Because if the fluid does not move, if you assume that the flow rate of the fluid is really, really slow, as if fluid does not move, you have high temperature wall on this side, low temperature wall on the other side, and in the middle is a stationary fluid, then it is simply conduction. Okay? So it turns to be the example of composite wall. You have high temperature, middle temperature, low temperature. Temperature profile would be conduction only. By using Fourier law, conduction only, when you integrate it, you get linear temperature profile. I show you that in the second example already. Okay? But for this particular example, if there's a movement of fluid, then it is not pure conduction. You add another term, the other term would be convection. So that would make the equation for energy to be nonlinear. So in reality, the temperature profile here is supposed to be nonlinear if you're taking account of the movement of the fluid. Okay? So this is the same situation that we have momentum transport and energy transport at the same time. The question is, we cannot solve them simultaneously. Which one should be solved first? Okay? So on one hand, I told you that if we start with momentum, if you start with momentum, the equation for momentum is supposed to have velocity, coordinate, x, y, and z, maybe time, right? And then it should have properties like density, viscosity. Okay? On the other hand, if you look at equation for energy balance, of course there will be temperature, coordinate, time, maybe. Then what? Of course, there will be density because convection term has density in it. There will be enthalpy, right? What else? Maybe gravity, right? The problem is these two will be function of temperature, and the flux itself, energy flux, is conduction flux plus this term V plus tau dot V. Okay? Energy flux is a function of velocity. So in this case, you see that velocity appears here. So, same thing. We have to start somewhere because we cannot solve these two equations at the same time. If we do the same thing as last examples, if we assume that density and viscosity is not a strong function of temperature, we can start solving momentum balance first, get velocity, plug it back in here, and then solve for temperature profile, just like last example. However, if you said that density and viscosity is not a strong function of temperature, then what we discussed over there for natural convection is gone. There's no point discussing natural convection at all, because natural convection is caused by the difference in density. So if you are interested in the movement by means of difference in density, you have to say that density is significantly changed with respect to temperature. Right? Otherwise, there's no point asking about natural convection at all. If you ignore that density is function of temperature, that means you treat this problem as pure conduction. There's no movement at all. Okay? So in this case, you cannot start by solving momentum balance. On the other hand, if you consider movement of the fluid by means of the difference in density, you see that the flow rate is really, really slow. If you try to see the movement of balloon lifting up, it's rather slow. The difference in density does not cause high velocity. So if velocity is low, then I can assume at this moment, if you look at the combined flux here, we can assume that this term, the convection term, is not so significant compared to the conduction term. So in terms of energy transport, the main mechanism is still conduction. Okay? So in that case, we can assume this term to be negligible in the sense of the calculation for temperature transport or temperature profile. For the calculation of temperature profile, we will assume that conduction is dominating, find the temperature profile, and then plug it back in here for the momentum balance equation to find velocity profile later. So for these examples, we will start with energy balance, and then followed by momentum balance. Understand? So as I said, there's no fixed rule where to start. You have to analyze the problems and start somewhere that assumption makes sense. Okay? So if we want to start with energy balance, we have to analyze temperature as a function of coordinate. In this case, if the whole wall has constant temperature, there's T2 everywhere, T1 everywhere. So that means temperature does not change with respect to Z. It's not function of Z. And this picture is two-dimensional. I disregard x-axis. I assume that temperature is uniform across this direction as well. So it's not function of x. Temperature is changing with respect to y. If you move your finger from left-hand side to right-hand side, temperature is changing, right? So it's function of y. Under this assumption, your shell is supposed to be thin in y direction. Okay? So that means my energy balance or energy shell is supposed to look like this, with the thickness of delta y. That's energy shell. Okay? And then, just like every time, we will assign flux going along the direction that we put for the origin point. Y-axis going this way, so there will be heat transfer or energy transport in y direction. That's combined flux in y direction, EY. Okay? Going in at y, going out at y plus delta y. Okay? So we have input minus output plus the term from the work from external force plus energy production equal to 0. That's shell balance for energy. Okay? Input is this term. It's basically flux itself multiplied by the area perpendicular to the flux. Okay? So if I said the wall has the width of W, the length of L, the area would be WL. Okay? And again, the area for input flux and output flux would be the same. So output flux would be like this. For external force, this is external work by gravity. And do we have one? You have to imagine, although in this problem you see that the movement going up or down is caused by difference in density, which is related to gravity. But in this case, we are doing shell balance for energy. Does gravity make temperature change? No, not in this case. So in this case, external force or external work by gravity is negligible. Gravity does not make temperature change. Okay? So we ignore this term. There's no external work like electricity, no non-mechanical work in this case. So we will ignore this term. Okay? So it will be 0 as steady state. If you divide the whole equation by WL, this term will be gone. If you divide it by delta Y, taking limit delta Y approaching 0, you end up with minus dEy by dy equal to 0. Okay? For energy transport, the balance is usually this way. It's usually simple. The complication comes from E itself, because you have to plug this E into this equation. Okay? So if I write EY, that will be Y component of the combined flux. Remember, Y component of this vector. So this is vector, Y component will be QY. This is also vector. Everything in the parenthesis is scalar, remains the same. Okay? Just Y component will be Vy only. So here, whatever inside parenthesis remains the same. And you plug Vy in here. This term is basically, if I write it here, when you write for Y component, the first subscript for tau should always be Y. So you start with Yx, Yy, Yz. Okay? And this V, which would vary from Vx, Vy, Vz. So this would be the flow work term. Okay? So before plug everything here in the differentiation over there, you just have to remove which term will be 0 first. And you see that in this case, Vy is 0. Okay? So if we look at the problems and try to see velocity components, okay, if we analyze it a little bit, velocity supposed to have Vx, Vy, Vz. Which one is 0? There's a flow in up or down direction, so therefore Vz is not 0 for sure. Okay? Is Vx 0? If there is a Vx, then there must be velocity component in this direction. If there's Vy, there will be velocity component in this direction. Is there any? No. So Vx is 0, Vy is 0, There's a Vz only, and Vz itself supposed to be a function of y for sure, right? You can see that velocity is going up on one side, going down on the other side, so it varies with respect to y. And as I said, the system is really long. Velocity in z direction is supposed to be constant, does not change, there's no acceleration. So in this case, it's not function of z, it's not function of x, it's a function of y only. Okay? Keeping that in mind, when we look into this combined flux for energy, we can say Vy is 0, Vx is 0, Vy here is 0, Vz is not. But Vz itself can be expanded using Newton's law. No, I'm sorry. Tau z. Tau yz can be expanded using Newton's law. Tau yz equal to minus mu dvz by dy plus dvy by dz. Okay? And we can eliminate this Vy term because it is 0. So essentially, if I erase this for the moment, rewrite the equation, I will get Ey equal to Qy, which is replaceable by Fourier law. Qy would equal to minus k dt by dy, according to Fourier law. That's conduction term. This term is 0, convection term is 0. Flow work term, you have only one term left, which is minus mu here, dvz by dy. Okay? Now, I changed this Vz, differentiation of Vz into total differentiation because Vz is function of y only. Then you can bring this equation to that shell balance and solve for temperature profile. If you do that, you see a problem right away. This is your problem, right? Because velocity is unknown at the moment. If you plug it over there, you cannot integrate. So our plan still needs something else. Okay? What do we need? We need to eliminate velocity somehow. How? First option would say, let's ignore this. Let's say velocity Vz is 0. It's so slow, it's 0. Can we say that? No, it's not 0. Okay? But if you realize, you see this is conduction. What is this term? I introduced this term in last examples. The whole term here is viscous heat. It's an increase in energy by means of flow work, right? So this one is viscous heat. And I told you last time, viscous heat would be dominating in two special circumstances. First, velocity is so fast, just like meteorite entering atmosphere is burning up. Second, viscosity is so large, just like in extrusion of polymer. On those two circumstances, that viscous heat become dominating. In this case, it is natural convection. Fluid is moving slowly by means of difference in density. So velocity is so slow. Viscosity is not significantly large because we talk about regular fluid. So comparing between conduction and viscous heat for this example, we can say that viscous heat term can be neglected. Please keep in mind, we are not neglecting velocity term. We just said that velocity is so low, the flow work term is not comparable to conduction term. Okay? So then, the flux becomes simple enough. You plug back here. I have minus here. I have minus over there. Then it turns to be plus d squared t by dy squared equal to 0. If you integrate this twice, the k itself can be eliminated because this right-hand side is 0. Okay? If you integrate it twice, it turns to be linear equation. T equal to C1y plus C2. Right? So you see that this is linear temperature profile, which means if I plot the temperature profile, it looks like this. Okay? It is linear because this is one-dimensional conduction. Whenever we have one-dimensional conduction in rectangular coordinate, it will be linear, just like in composite wall. Okay? You don't have to do this at all if you understand the problems and you said from the very beginning that the flow is so slow and I am going to assume this one to be linear. If it is linear, it means I'm implying conduction dominating. Right? You get this linear line right away. But mathematically, once you get this, we need to find C1 and C2. We need two boundary conditions. Of course, we know temperature T1 and T2 already, so we just plug it in to solve for temperature profile. All right, so boundary condition at y equal to, the width of the gap is 2b. So on the left-hand side, that's y equal to minus b. Okay? Temperature is equal to T2. So I will have T2 equal to C1 times b minus plus C2. Another boundary would be on the other side of the wall. At y equal to plus b, temperature is T1. Then you have T1 equal to C1b plus C2. Two equations, two unknowns, you can solve this one directly. Okay? If you combine these two equations, the first term will be eliminated. Then you get C2. So C2 would equal to T1 plus T2 over 2, right? You add these two equations together. This term cancels out. This term turns to be 2C2. This one is T1 plus C2. And according to definition, this is one temperature added by another divided by 2. That's average temperature, right? So it is average temperature. Basically, if function is linear, this temperature is located at the center. Then you can solve for C1. If you plug in and solve for C1, then you get C1 equal to 1 over b times 1 over 2, T1 minus T2. Okay? Replace that into the temperature profile equation. You get temperature equal to linear temperature, average temperature minus half T2 minus T1 Y over B. And this can be said to be delta T. Okay? It's a linear temperature profile like that. Now, if we are interested in temperature profile, this is the answer, this is it. We can stop. But of course, we are interested in something else. We want to know velocity profile as well. Okay? So now we have to do shell balance for momentum. For momentum, we already analyzed that velocity component that is non-zero is Vz. And Vz is function of y only. Okay? So if Vz is function of y only, that means our shell supposed to be thin in y direction, supposed to be full size in x and z directions. So if you draw the shell for momentum balance, it looks the same. So this would be your shell for momentum balance, right? And there'll be a flow, a flux going in and out. In this case, since velocity is in z direction, the flux here is supposed to have the second subscript to be z. So this is flux in z momentum transferring in y direction. So transferring in this y direction. Okay? So we have phi yz going in and out. And there will be phi zz going in and going out. This is zz. Okay? We can ignore x direction because we draw this one as two-dimensional. Just ignore x for the moment. So, I'm going to do the same thing as what we did in momentum transport. Okay? Phi yz, that's supposed to be tau yz, the molecular transport for momentum, plus convective transport rho vy vz. Right? Phi zz, that would be tau zz, plus rho vz vz, plus pressure term. Whenever you have same subscript, you need to add pressure term. Okay? Then, we know that velocity Vy is 0. Velocity Vz is not 0. If we expand tau term, that would be minus mu dvz by dy plus dvy by dz. And this Vy term will be 0. So according to this, phi yz is not 0. So this term must be used in the balance. For zz, tau zz is minus mu 2 times dvz by dz plus 2 over 3 mu minus k del dot V. Right? If our fluid is liquid, this is incompressible, this term will be 0. It will be 0 according to equation of continuity. Remember? We said every time when we have liquid or incompressible fluid, this term will be 0. And Vz itself is not function of z, it is function of y. So the whole term here turns to be 0. So that means this term is 0. We only have this convective transport in z direction and pressure. Let me keep this equation somewhere. All right. So, plug this in the momentum balance. Input term, let's start with YZ. The area perpendicular to flux YZ is WL. Inside, there will be, let's do it the regular way. Phi YZ at Y minus phi YZ at Y plus delta Y. That's a YZ direction. Plus ZZ direction. The area is supposed to be W times delta Y. Right? W would be area perpendicular to this screen. Delta Y is this gap. Okay? Then inside that would be ZZ at Z equal to 0 minus ZZ at Z equal to L. That's in and out in two directions. And then external force by gravity. Now in this term, we have to add it because gravity causes the flow. Flow is related to gravity. Earlier in energy transport or energy balance equation, we ignore gravity term because gravity does not change the temperature. Okay? So the gravity term is supposed to be volume times densities times G. Volume would be volume of the whole shell, which is WL delta Y times rho times G. In this case, G is supposed to be negative because our axis is going up, gravity is going down. So G will be negative, equal to 0. Okay? For the first pair, if I divide the whole equation by WL, this WL will be gone. I'm going to have L over here, W will be gone, WL will be gone here. If I divide the whole equation by delta Y and I change phi to tau, the first term would be tau YZ minus tau YZ as Y plus delta Y over delta Y, right? We determined earlier that phi is basically tau because Vy here is 0. So plug it back here. This term, we have 1 over L. This term turns to be rho VV only. So inside you have rho VZ squared at Z equal to 0 subtracted by rho VZ squared at Z equal to L. Plus the pressure difference term P0 minus PZ or PL. minus rho g equal to 0. Now we have familiar equation. This equation has been shown to you in the first session of momentum. Right? During that time, we said this term turns to be 0. Why? Because Vc is function of y. It's not function of z. So Vc here and Vc there supposed to be the same. It does not change with respect to z. So it's cancel out. They cancel out. Okay? Pressure term, can we ignore pressure? Can we drop these two terms? Can we say P0 and PL canceling each other? Now let's go back to the picture. P0 is here, Pz is there. Do you think pressure is different? Yes, they are different. There's a head of liquid pushed on top of each other. So pressure down here is supposed to be higher than pressure over here, even though we did not supply any pressure. So pressure is not canceling each other. Okay? From this part, if you take limit delta y approaching 0, the first term turns to be differentiation of tau yz by dy plus pressure difference over L minus rho g equal to 0. Okay? And if I replace this tau by Newton's law that we determined earlier, that the second term is already eliminated, tau itself is minus mu dvz by dy. Okay? Plug it back here, minus and minus cancel out. I get mu d square vz by dy squared. In our momentum session, we combine these two together to get the modified pressure. Okay? But in this case, I want to keep it this way. Just for the moment, I will discuss later. If I keep it, I will get this equation. The reason that I keep it at this time, I did not combine this with pressure, simply because this density is now function of position. Right? So density as 0 position and at L position are not the same. So I keep them separately for the moment. So you have to keep in mind that now density here is a function of temperature. So in order to solve this equation, if somehow you can integrate this equation, you get velocity profile as a function of y. Okay? But in order to do that, you need to know function of density with respect to temperature. So you either use thermodynamics or approximation. Now, because using thermodynamics is way complicated, in this case, I am going to make approximation, simple approximation. Of course, you have to keep in mind from this step now on, basically this function can be described using equation of state, the EOS in thermodynamics. You can pick any EOS that is proper for your system. Okay? But for the sake of simplicity in this problem, I'm to make approximation of my own EOS. So I'm going to use what we call Taylor series expansion. And I'm going to use only first order. According to Taylor series expansion, any variable which is changing can be calculated using one value at fixed point added by differentiation at that point, right? If I choose the fixed point to be where temperature is mean temperature, differentiation here is supposed to be differentiation with respect to temperature multiplied by the deviation from the average point. So again, let's say this is y, this is x. You pick y as known x plus the slope at that point multiplied by the deviation in x. That's Taylor series expansion. If you use second order, the second term or the third term here will be second order derivative and so on. So let's make things simple using first order. Okay? This slope here is supposed to be slope at the fixed point that we chose. Of course, we cannot avoid thermodynamics. According to thermodynamics, if I put down here, we have one variable called the coefficient of thermal expansion, beta. Beta was defined like so. This is pure thermodynamics. And this beta, according to what we learned in thermodynamics, is commonly used for liquid. Okay? So if this is specific volume, we can convert this specific volume to density. It is just inverse of density. So this is basically 1 over rho d 1 over rho dt at constant pressure. Okay? So if you take differentiation over here, you get minus 1 over rho d rho by dt at constant pressure. Okay? Because this is differentiation of the inverse. So that means this density at known temperature, at average temperature, if I call this one rho bar, let's say this one is known number at fixed point, and we discussed that at T bar is supposed to be at the center. Okay? d rho by dt can be calculated based on here. This is d rho by dt. Okay? Of course, according to thermodynamics here, pressure is supposed to be constant. But if we assume that pressure is not changing much with regarding to the system here, we can take this term, the whole term here, to be rho times beta, right? If you move rho to the left-hand side, you get rho beta or minus rho beta equal to d rho by dt. So this term is going to be minus rho beta. times T minus T bar. Of course, the whole differentiation terms is taking place at T bar. So this rho would be rho bar. The beta would be called beta bar as well. Now everything with bar is supposed to be fixed number, supposed to be constant. Okay? So now we have simple equation telling density with respect to temperature. This is my equation of state. Of course, you can use other equation of state, but this one is simple enough. Okay? All right? And from energy balance, earlier, we got this equation. That's temperature profile. If I rearrange the equation a little bit, we can see that T bar is on the right-hand side here. If I move T bar to the left-hand side, that's this term. Okay? So according to energy balance or temperature profile, I get T minus T bar equal to 1 over 2 delta T y over B. So the red equation is basically temperature profile that we found from energy balance. So now we are incorporating energy balance into our profile. Okay? So I'm going to copy my equation, mu d square Vz by dy square plus pressure minus this rho g term. Now I'm going to use the equation of state that we just derived. So rho g will be split into rho bar g minus rho bar g beta bar delta t over 2 y over b equal to 0. Now you see that in this equation, we have temperature hiding in this delta T, right? But temperature is already known here. Temperature is already a function of y. So if you integrate this equation, you get velocity as a function of y. That's velocity profile. But the equation itself is rather complicated at the moment. Okay? So we want to simplify this a little bit. Now, if I want to compare between these two groups, pressure groups and density or heating group, okay? If I look at the picture, the fluid, this is pressure P0. On top, that's pressure PL. And there's a gravity or weight of the liquid itself. So if you do the free body balance of the liquid itself, you have this picture. If I do the force balance, I will get that force pushing down That's pressure times cross-section area 2b, which is the whole width, multiplied by the distance perpendicular to the screen. Okay? So this is force pushing down. I'm sorry, pushing up. P0 is pushing up. That should equal to force pushing down plus mg. Right? And this m is supposed to be volume times density. The volume would be 2BWL times density rho. Of course, density is changing with respect to position. If I redraw the picture. Okay? Density is changing with respect to position here. So this term is not constant, it's varying with the position. But on average, we can say that the whole mass can be represented by average density, because it's high density down here, low density up there. So on average, it's supposed to be, normalize each other. So if you make approximation to be rho bar at this point, you see that 2BW canceling each other, and you will have P0 equal to PL plus rho bar GL. In other words, P0 minus PL over L should equal to rho bar G. Of course, this equation is approximation because we approximate by rho bar. In detail, density is changing. They're approximately the same. So if we use this approximation, we can see that this term is approximately 0. But in detail, if you want to derive and eliminate this, maybe you can have 4 more pages. But we can do that. Okay? So from here, basically you need integration. Let me erase this. If we integrate, moving this to the right-hand side, integrate it first, I will get dvz by dy equal to everything on the right-hand side, that's rho bar g beta bar delta t over 2. I move mu to the denominator. I have y. After integration, you get y squared over 2 and b over here, plus another constant. If I integrate again, I get vz. Now y turns to be y cubed over 3b plus c1y plus c2. Okay? The rest is basically plugging in the boundary condition. And we know two boundary conditions. First boundary is at y equal to minus b. What is Vz? Zero. Under no slip condition, it is zero. Okay? Another boundary condition would be at y equal to plus b, Vz is zero again. Two boundaries, two unknowns. You can solve for this, and that would be your velocity profile. Okay? Any question? Keep in mind that delta t here is t1 minus t2. It's constant. It's not changing with respect to position. The whole term, everything in here is constant. All right? So we have 15 minutes left. I want to start another example just for the description of the problems because it's somehow linking to these problems. Okay? And on the calculation detail, I will give it on next week. The problem is basically circular pipe, okay? And it can be hot water going in, and then during flowing, there'll be heat transfer outside because outside air is colder. So hot water has higher temperature, cold air has low temperature. Difference in temperature is a driving force for heat transfer. So there will be energy transport from in radial direction. Okay? In the same time, if you have hot water going in, you can imagine down here, temperature of water is supposed to be lower. So there will be energy transport in z direction as well. So if I put the axis like this, we have z-axis, r-axis, r from the center to the circumference. Okay? Now we have energy transport in two directions. One is in r direction for sure. Another one is in z direction. If you imagine a group of water flowing down, this group of water carries energy. So there will be convective transport in z direction, right? Because first, in order to determine whether we have convective transport or not, you have to look into the direction, let's say in z direction here, whether you have differences in temperature or not. In this case, temperature up here and down here are not the same, and there's a flow in this direction. So there must be convective transport in z direction. Okay? It is different than last example. Example, on Tuesday, we have movement v here, okay? And there's a velocity profile. And this is T0, TB. In this example, this is X, this is Z, okay? Is there any convective transport in Z direction? In this example, if you look in X direction, there's an energy transport for sure, right? High temperature, low temperature, there'll be energy transport in X direction. Is there any energy transport in Z direction? In this problem, temperature here, if I draw this shell, temperature over here and temperature over there is supposed to be the same. Remember, this is small part of the whole bearing. If temperature on these 2 points are not the same, it cannot it cannot come back to the whole circumference. Okay? We decide during that time that these 2 points are supposed to have the same temperature. So even though you have velocity in Z direction, there is no temperature difference in Z direction. So in this case, there is no convective transport in Z direction. If you recall what we discussed on Tuesday, the flux, the convective transport flux in this problem is 0. Okay? In this problem, we only have flow work. We don't have convective transport. So whether we have convective transport or not is not solely depend on velocity. It depends on temperature difference as well. This problem, on the other hand, you see that temperature here is higher than temperature over here because you have energy loss from hot water to the cold air. So water here is hotter than water down here. So in Z direction, you have temperature difference. You also have velocity in Z direction. So in this case, there is convective transport in Z direction. Okay? What about this problem? Do we have convective transport in Z direction? No, we do not have convective transport in Z direction in this problem. Remember the flux? The convective flux is, if we calculate EY, right? This is EY. That's supposed to be QY plus something here times VY plus rho dot V for Y component. Remember? This Vy is 0. Because now Ey is in this direction, even though there's temperature difference in Y direction, but there's no flow in Y direction. Okay? So this problem, or these examples, would be the first one that convective transport is dominating. Okay? This is called forced convection. We force the flow, and the flow causes convection. This is natural convection. This is forced convection. Okay? The point that I want you to see is that, of course, this one has momentum transport as well as energy transport. Now in this problem, we're supposed to solve momentum first. Why? For momentum, the key is density and viscosity is a function of temperature. For energy, basically convection is a function of velocity. In this case, of course, flow work is also a function of velocity. Okay? In this case, you have learned from unit operation 3 that convection is more effective than conduction, right? In heat exchanger, in order to increase heat transfer coefficient, you have to increase velocity. That's why heat exchanger is usually operated under turbulent, because the velocity is higher. So now convection is dominating. That means this term is really important. Okay? In order to calculate this term, we need velocity. So we cannot ignore convection to calculate velocity, just like the previous example. We cannot do like this anymore. In this part, we ignore convection to get temperature profile first and plug temperature profile to find velocity profile. We cannot do that in this example because convection is really important in this problem. So the only way to do this problem is to solve momentum first and get velocity profile, plug it in here. In order to solve momentum first, you have to do it under assumption that density and viscosity is not a strong function of temperature, which makes sense if temperature is not significantly different. Okay? Now, if we start with momentum transport, the shell, we have velocity, VR, V zeta, Vz, okay? And this is flow in pipe, there's no VR, there's no V zeta. Vz itself is a function of R only. We discussed this already in the momentum part. And the shell for momentum calculation looks like this. Right? Vc is function of R only, so the shell is supposed to be thin in R direction, supposed to be full size in theta and in Z. So this is shell momentum, the shell for calculation of momentum. For energy, however, now you see that temperature is function of R for sure. Inside, at the center, temperature is supposed to be higher than outside because at the wall, it is somehow connected to cold air. So temperature would change in R direction, for sure. So there'll be temperature change in R. Temperature is function of R. Without temperature change in R direction, there will be no heat conduction in R direction. And we have to, we realize already that there's a conduction in R direction. So we have to allow temperature change in R direction. Okay? According to symmetry, it's not function of zeta. Temperature is the same around the circumference. Temperature is changing with respect to Z as we discussed earlier. So now temperature is function of R and Z. So that means shell for energy calculation or energy balance supposed to have the thickness of delta R in R direction, thickness of delta Z in Z direction, and cover full size 0 to 2 pi in theta direction. What does it look like? Now it looks like this. Okay? So this is delta R, this is delta Z. So this is the first problem that shell for momentum and shell for energy are not the same. And I said from the very beginning that they are not necessarily the same. All right? So I'm going to stop here, and the calculation will continue next week. Any question? Okay, so if there's no question, the calculation continues. So see you next week.